We now begin to study polynomial functions. First, we look at what a power function is. So a power function is a function that can be represented in the form of f of x equals kx to the p, where both k and p are real numbers, and k is known as the coefficient. So some common power functions are given in this table. We have the constant function, which is f of x equals some constant number. We have the identity function, which is just f of x equals x. We have the quadratic function, which is f of x equals x squared. We have the cubic function, which is f of x equals x cubed. We have the reciprocal function, which is f of x equals 1 over x. We have the reciprocal squared function, which is f of x equals 1 over x squared. We have the square root function, which is f of x equals square root of x. And we have the cube root function, f of x equals the cube root of x. Right, so if we look at the powers, the power of the constant function is 0. Power of the identity function is 1. Power of the quadratic is 2. Power of the cubic is 3. The power of the reciprocal is -1. The power of the reciprocal squared is -2. The power of the square root is 1/2. And the power of the cube root is 1/3. Now the behavior of a function as x gets very large in the negative direction, which is represented x going to minus infinity, where x tends to negative infinity, or very large, written x tends to infinity, is referred to as the end behavior of a function. So the end behavior, as it says, is what the function is doing on the very ends. So as x goes to minus infinity or x goes to positive infinity. So the end behavior of the power functions, if the coefficient is positive and it's an even power, then you can see that as x tends to minus infinity, f of x will tend to infinity. As x tends to positive infinity, f of x will also tend to positive infinity. So when k is positive and it's an even power, the function tends to infinity on both ends. If k is positive and now we have an odd power, so as x tends to minus infinity, so will our function. As x tends to positive infinity, so will our function. So if k is positive and it's an odd power, then the function tends in the same direction as x tends. Finally, if x is negative, then we just have a reflection. I'm sorry, not x. If k is negative, then we just simply have a reflection about the x-axis. And so what f of x does just reverses. So we're going to go ahead and describe the end behavior of each of the following power functions. So for f of x equals x to the 8, right, our k, our coefficient is 1, which is positive. Our power is 8, which is even. So our function x to the 8 will tend to infinity as x tends to negative infinity, and x to the 8th will tend to infinity as x tends to infinity. Now we have negative x to the ninth. So our coefficient k here is -1. That's obviously negative. That's less than 0. Our power is 9, which is odd. So x to the ninth would normally tend to minus infinity as x goes to minus infinity, but we have a negative coefficient, so this will tend to positive infinity as x tends to negative infinity. And x to the ninth will tend to minus infinity. I'm sorry, negative x to the ninth will tend to minus infinity as x tends to positive infinity. Now, if we take a linear combination of different power functions, we get what's called a polynomial. So let n be a non-negative integer. A polynomial function is a function that can be written in the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus so on and so forth plus a sub 1x plus a sub 0 or a naught, where each of the a sub i's is a real number and the leading coefficient, this a sub n, is not 0. So this form right here is known as the general form of the polynomial. N is the degree of the polynomial, so the degree is the largest power that appears. Each of the a sub i's are called the coefficients, where a sub n is the leading coefficient. Each product, a sub I x to the I, is called a term of the polynomial. This first term will be called the leading term, and this final term is the constant term. Now, the end behavior of a polynomial is how the leading term behaves. So since the leading term is simply a power function, we can use the previous chart to determine the end behavior. And to see why it's as the leading term behaves, we can just look at several examples. Right? So if we just look at, let's say, x to the 1000 plus 2x to the 999 plus 5x, let's say. Remember, end behaviors, x is getting very large or very small. It's very large in the negative direction. Right? So if we say, well, let x be 1 million. Well, if we look at 1 million to the 1000 versus 1 million to the 999, right? This term, this leading term, completely dominates everything else. Nothing else really matters. So this is why the end behavior is determined solely based on this leading term. So here are some examples. We have the polynomial 5x to the fourth plus 2x cubed minus x minus 4. Its leading term is 5x to the fourth. So this means that the end behavior is going to be determined by the power function 5x to the fourth. Well, this is an even power function with a positive coefficient, so the end behavior will be positive infinity, as x tends to both minus infinity and positive infinity. Okay. So next up we have the polynomial negative 2x to the 6th minus x to the 5th plus 3x to the 4th plus x cubed. Well, this leading term here is the power function negative 2x to the 6th. That is a power function with even power and negative coefficient. So it will tend to negative infinity, as x tends to both minus infinity and positive infinity. Next up, we have the power function the polynomial 3x to the 5th minus 4x to the 4th plus 2x squared plus 1. Now this leading term is 3x to the 5th. That is a power function with odd power and positive coefficient. So f of x will tend to minus infinity as x tends to minus infinity, and will tend to positive infinity as x tends to positive infinity. And finally, we have the polynomial negative 6x cubed plus 7x squared plus 3x plus 1. This has a leading term of negative 6x cubed. So this is an odd power function with a negative coefficient. This graph is completely wrong, so ignore it. Right, so this function, I'll write it out, f of x will tend to positive infinity as x tends to negative infinity, and f of x will tend to negative infinity as x tends to positive infinity. Right, so a continuous function has no breaks in its graph, and a smooth curve is a graph that has no sharp corners. And polynomial functions are both continuous and smooth. Furthermore, a polynomial function of degree n will have, at most, n x-intercepts and n minus 1 turning points. So a turning point is simply a point where the graph is turning. Right. So if we look here, right? So right around here would be a turning point. You can see the graph turns, and then also right about here will be a turning point because the graph is turning again. So determine whether the given graph is a polynomial function. So here we go. So remember, what we're going to be looking at is it continuous and is it smooth? Well, this is continuous, right? There are no breaks in the graph. And it's also smooth. There's no sharp edges. So this is indeed a polynomial function. All right, we look at this one. Well, it's definitely continuous. However, it has a sharp edge right here, which means this would not be a polynomial function. Once again, this is continuous, and it's got no sharp edges, so it's also smooth. So this would be a polynomial. Well, this one is smooth. There's no sharp edges, but look, there's a graph. It's not continuous. And so this would not be a polynomial function. we're laying the groundwork now for graphing polynomial functions. However, the end behavior only describes what's happening on the ends. It gives us no information about the middle of the function, right? So if I look back here, the end behavior is only telling us how the function tends in either direction. It does not give us any information basically about this shape here. This is what we call the middle of the graph. Well, we can determine how the middle behaves by examining intercepts and the turning points. And I already defined what a turning point is, but here it is again, more formally. A turning point of a graph is a point at which the graph changes from increasing to decreasing, or from decreasing to increasing. So to determine the y-intercept, remember all we're going to do is plug x equals 0 into the function. So note that by definition of a function, there can be at most a single y-intercept. Because if there is more than one y-intercept, it would fail the vertical line test. Right, to give you an example, right, let's look at this function, or this graph rather, right? It has two y-intercepts, but it's failing the vertical line test, which means this cannot be a function by definition. So at most, there's only a single y-intercept. To find the x-intercepts, we must solve f of x equals 0 for x. Now when we solve this, or when we're solving a polynomial of this form, f of x equals 0, there are several possibilities. The first is that the polynomial can be factored using known methods from algebra. The second possibility is that the polynomial is already in factored form. The third possibility is we'll just use technology. And the fourth possibility is that the polynomial must be factored using polynomial division techniques. Now, throughout the remainder of this lesson, only these first three will be considered. The next lesson will consider this fourth possibility. So in the next lesson, we will delve into polynomial division and then look at how to factor polynomials. So for now, let's look at several examples of finding intercepts of polynomials. And remember, these examples are going to focus only on these first three possibilities. So here's our first function, x to the 6th minus 3x to the 4th plus 2x squared. So remember, to determine the y-intercept, all we do is evaluate f of 0. So that's just 0. So the y-intercept would be 0, 0. To find the intercepts, we must solve f of x is equal to 0. So this means we have x to the 6th minus 3x to the 4th plus 2x squared is equal to 0. Well, if we look at each term, there is an x squared common. So we can factor out an x squared. We'll be left with x to the 4th minus 3x squared plus 2 is equal to 0. Well, now, this term in here can be expressed as a quadratic, right? This is x squared squared minus 3x squared plus 2. So each grouping will have an x squared common, and remember we're looking for factors of 2 when added give 3, well, 1 and 2, plus tells us that both will have a minus. So it's factored x squared minus 1, and x squared minus 2. This, of course, then means by the zero property. The zero property states that if you take the product of real numbers and it's 0, then at least one of those numbers must be 0. So x squared has to be 0. Or x squared minus 1 has to be 0. Or x squared minus 2 has to be 0. Or possibly all of them are 0. So this would mean x has to be 0. Or if we solve this, we get x is plus or minus 1. Or x is plus or minus the square root of 2. And so all of our intercepts so we have negative square root of 2 comma 0. Then we have negative 1 comma 0. Then we have 0 comma 0. Then positive 1 comma 0. And finally positive square root of 2 comma 0. So this one right here, this middle term, this middle intercept happens to be both a y-intercept and an x-intercept. Next up, let's look at x cubed minus 5x squared minus x plus 5. So the y-intercept, f of 0, in this case is just 5. So now for the x-intercept, we have f of x is equal to 0, which means that x cubed minus 5x squared minus x plus 5 has to be 0. And now what we're going to do here is a technique that's known as factoring by grouping. So let's group the first two terms and the second. Right, and then there'll be a plus in there. So from the first grouping, we can factor out an x squared. And we're left with x minus 5. Now the idea behind factor by grouping is we want to factor something out now of the second group so that we get x minus 5. Well, we can factor out a minus 1. So minus, and then we're left with x minus 5. Now there's an x minus 5 common, so we can factor that out. And we are left with x squared minus 1. And we can go even further. X squared minus 1 is the difference of squares, so we can write that as x plus 1 times x minus 1. So again, by the zero property, we have to have x minus 5 being 0, or we have to have x plus 1 being 0, or we have to have x minus 1 being 0. Which means that x is either 5, negative 1, or positive 1. And so, our intercepts we have -1, 0, and we have 0, 5. That's the y-intercept. Then we'll have 1, 0, and finally 5, 0. Now let's look at this polynomial. So for the y-intercept, f of 0, so we're going to have -2 squared times 3, which is 4 times 3, that's 12. Let's look at the x-intercepts. So we have to have f of x is equal to 0. So this means x minus 2 squared times 2x plus 3 must be 0. This is already factored. So we have to have x minus 2 squared being 0, or 2x plus 3 being 0. Well, this means that x minus 2 must be 0. And so what we have is x is either 2 or -3/2. So the intercepts -3/2, 0, 0, 12, and 2, 0. So we now want to use technology to determine the intercepts of this polynomial. So this example, since it's using technology, will be covered in a different video, one that gives a tutorial on how to determine intercepts using technology. So now we have to examine the behavior at the intercepts. The graph may behave differently at the different x-intercepts. So there are two possibilities. The graph can either pass right through the intercept or just touch the intercept. That is, it'll turn at the intercept. So the intercept is a turning point. How the graph behaves at the intercept is determined by the multiplicity of the 0. So if a polynomial contains a factor of the form x minus h to the p, we say that x equals h is a 0 of multiplicity p. Informally, the multiplicity of a 0 is how many times that 0 occurs in the polynomial. So let x minus h to the p be a factor of the polynomial f of x. If p is even, the graph will touch the x-axis at h. If p is odd, then the graph will cross the x-axis at h. And we are now in a position to graph a polynomial function, at least sketch the graph. Now, this is only going to be a very rough sketch. When you study Calculus 1, you will study how to graph functions way more accurately than what we can do in this course. So the first thing we want to do is find the intercepts of a polynomial. Then check for symmetry. Then use the multiplicities of the zeros to determine the behavior of the polynomial at the x-intercepts. Determine the end behavior. Then we can use 2, 3, and 4 to sketch the graph. And finally, we should ensure that the number of turning points does not exceed 1 less than the degree of the polynomial. So we're going to sketch the graph of this polynomial. So the first step was to determine the intercepts. So the y-intercept, f of 0, we get -2 times +3 squared times -5. So we have 10 times 9, which is 90. The x-intercept, we're going to have -2 times x plus 3 squared times x minus 5 being 0. So this means that x is -3 or x is +5. And so our intercepts would be -3, 0, 0, 90, and 5, 0. Second step is to determine symmetry. So we want to do f of -x. This will give us -2 times -x plus 3 squared times -x minus 5. If we factor out a negative from the second term, we'll get +2 times, we can factor out a negative here and square it and it becomes positive, so this becomes x minus 3 squared times x plus 5. Notice there's no way to get this to equal either f of x nor f of -x. So there is no symmetry. Step 3 is to determine the behavior at the x-intercepts. So at the intercept, -3, 0. Well, -3 here, right, had a multiplicity of 2. So it just touches. And at 5, 0, it had multiplicity of 1, and so this crosses. Fourth, we were to determine the end behavior. Well, the leading term, so this will be x squared, x, so x squared times x is x cubed, times this -2. Leading term is a -2x cubed. So what this means is that f of x will approach positive infinity as x approaches negative infinity, and f of x will tend to minus infinity as x tends to positive infinity. So we are now in a position to do step 5, which is to actually sketch the graph. So here is my coordinate system. My x scale is 1, which means each tick will count as 1. My y scale is set at 15, so each of these ticks will count as 15. So first let's use the intercepts. So the y-intercept was at 90, so 15, 30, 45, 60, 75, 90. So right here's my y-intercept. All right, so we had two x-intercepts. We had one at -3, 1, 2, 3 right there. And then we had one at 5 right here. So the end behavior, as x tends to minus infinity, our function tends to positive infinity. So our function is going to have to start from way up here. So it's going to do something like this, and it's going to tend downwards towards our intercept. Now, at the intercept, -3, remember, had an even multiplicity, so this is a turning point here. So it's going to do something like this. And it's going to curve upwards. Now it has to pass through this 90 here. Now here's where the problem lies. We don't know whether 90 is a turning point or if the turning point is somewhere else, but we know it has to turn at some point so it can pass through 5. So I'm just going to assume it passes through 90 and then turns. And this is where calculus will come into play. In calculus, you'll be able to determine exactly where this turning point is. All right, so now it's going to come down to the x-intercept of 5. And 5 was odd multiplicity, so it passes straight through it, which is good because as x tends to positive infinity, our function tends to negative infinity. So there would be a sketch of our polynomial. And again, the polynomial was -2 times x plus 3 squared times x minus 5. Now the last step is just to check the number of turning points. So the degree of this polynomial was 3. Now, number of turning points we have. So here's 1, here's 2, and that's it. Well, 2 is no more than 1 less than 3. So that checks out, and so we're done. Now, like I said, when sketching a polynomial using pre-calculus techniques, it's not going to be a perfect representation. Right? As I said up here in this example, we have no idea where this turning point is. So I'm just guessing it's here. Using techniques of Calculus 1, I would be able to exactly determine where all the turning points are. And thus I'd be able to more accurately represent the true graph of this polynomial. Anyway, that concludes our study of polynomial functions. Do not forget to check out the tutorial on graphing polynomial functions to do that one example that required technology to find the x-intercepts. So that concludes our study of polynomial functions.